Okay, here we are with the second of our video lectures on quantum theory. And this time we're using a new technology, a new way to create this video. So I'll be very interested in your comments on how this works and whether these videos are as effective as the ones we've had before. So let's start out by reviewing some things we've done in class over the last week. The first thing I want to remind you of is Euler's formula. Euler's formula, which says that e to the I theta, e to the imaginary unit, the square root of minus 1, times a real parameter theta, is cosine of theta plus I times sine of theta. And this is one of the most amazing formulas in mathematics. We talked about this in class. We justified it based on power series and so on, but this is a really useful formula. And one way to think about it is this. If you imagine the complex plane as a kind of a two-dimensional vector space, then a complex number is a real number x plus I times another real number y. In other words, the real and imaginary parts of the complex number are sort of like the x and y components of the vector in the complex plane. And you can do calculations with the components. For example, if you want to find the modulus squared of the complex number, that's just x squared plus y squared. That's the length of that little vector, and that's equal to z star times z, where z star is the complex conjugate of z, which is x minus iy. You take all the i's and turn them to minus i's. Well, there's another way we can think about this. We can think about the magnitude and direction of this complex number arrow. We can call the magnitude r and the angle from the real axis theta, and then it turns out that the complex number is equal to r times e to the I theta. It's a different way of writing the complex number. It's the polar form of the complex number. And then we can also do calculations using this. For example, the modulus squared, the magnitude squared of the complex number, is just r squared. R is the magnitude. Okay, so this is a very handy way to think about complex numbers. And we can use this to think about oscillations in time. We can think of them as complex oscillations. We can write an oscillating factor as e to the minus I omega t. The minus sign is just convenient later on, but e to the minus I omega t. Well, what does that look like? Well, let's take a look in the complex plane. This e to the minus I omega t would be cosine omega t minus I sine omega t, which means it would be a vector of unit length that would rotate clockwise about the complex plane with an angular velocity omega. So this is great because the angular frequency omega is the angular velocity omega for this complex factor in the complex plane. So let's take a look at how that works out. We'll actually animate this in time. So we start out at time equal to 0 with e to the minus I omega times 0 being 1. And then that's all on the real axis. And then as time passes, the quantity rotates clockwise. And so on the left-hand side, we have what it looks like in the complex plane. On the right-hand side, we're tracing out both the real part and the imaginary part. The real part is red, and the imaginary part is blue. And we can see that both the real part and the imaginary part are oscillating, not together, not in an opposite way, but offset by a quarter of an oscillation. And so these two oscillations are sort of packed together in the single complex oscillation described by that e to the minus I omega t. But of course, we shouldn't really think about this complex oscillation as two oscillations, and we'll get to that in a moment. So let's now consider a complex wave in one dimension. The wave function f of x and t is a in amplitude times e to the I kx minus omega t. That kx minus omega t is a factor that we're familiar with from our previous analysis of waves. And so at time equal to 0, if we plot the real part in red and the imaginary part in blue, we get a couple of sinusoidal varying factors. The red one is like the cosine and the blue one's like the sine. And then that's at time equal to 0. And it has a wavelength equal to 2 pi over k. That's the distance between successive crests or troughs of the real part or the imaginary part. And then over time, this wave will propagate, will move with the phase velocity to the right, like so. Okay, but once again, we really don't want to think of this as two waves, a real wave and an imaginary wave. We want to think of it as one complex wave. Let's see if there's a way we can visualize it that way. Let's imagine instead of a single vertical axis for the wave function, we have a whole complex plane. This is sort of drawn obliquely with a real axis and an imaginary axis. And then we have the x-axis, the direction of propagation of the wave, this way. Then this complex wave will be a kind of a right-handed spiral in the direction of propagation. It will be a helix. It'll have a distance 1 from the x-axis, that's or a distance actually a from the x-axis, and as you move in x, the phase, the angle of where you are, changes. And over time, this whole spiral in the complex plane will shift along the x-axis as time gets larger and larger. So what we have is we have a kind of a way of thinking about this complex wave geometrically. In a three-dimensional picture, one dimension is space, the other two dimensions represent the complex plane. Okay, so waves are governed by something we call the wave equation. Let's review that. Let's imagine you have a wave function, which is f of x and t. That might, for example, represent the lateral displacement of a stretched wire, or it might represent air pressure in sound waves. In any case, this function is governed by a differential equation which involves partial derivatives with respect to both x and t. And that differential equation we found was of this form. The second derivative of f with respect to x is 1 over v squared times the second derivative of f with respect to t. And there's an awful lot to say about this wave equation. For example, the first thing is to say this is the equation of motion for the wave function. This tells you how the wave function changes over space and time, how those things are related to each other. And also, for mechanical waves, like the displacements of a stretched wire or even sound waves in the air, for mechanical waves, this wave equation always boils down to a version of f equals ma. That's why it involves the second derivative with respect to time. That's an acceleration term. So this is really a version, a disguised version of f equals ma applied to whatever it is, whatever mechanical system it is that is moving in the mechanical wave. And finally, note that this is a real equation. This equation doesn't contain I, the imaginary unit. It's nowhere to be found. You can talk about real solutions to this equation. Real as in real value. But nothing prevents you from also considering complex solutions. Okay, so let's take one of these simple complex waves that we talked about and see how it works out in the wave equation. To do this, we're going to have to take some derivatives. So we start out with our wave function, and when we take the derivative with respect to x, well, the derivative of the exponential is just the exponential. But when we take that derivative, we have to remember the chain rule, and so we get a factor of ik, the thing multiplying x in the exponential, out front. And if we take the second derivative, we get another factor of I times k. And so the second derivative of f with respect to x squared, which appears in the wave equation, is just minus k squared times f. Notice what happens when we apply derivatives to this simple wave. Every time we apply a derivative with respect to x, it's just like multiplying whatever we have by I times k. There's a kind of correspondence between taking a derivative and multiplying by I times k. And in a similar way, we can take derivatives with respect to time. And every time we take a derivative with respect to time, we get a factor of minus I omega. The exponential stays the same, but the chain rule gives us an extra factor out front. And so that gives us that the second derivative of f with respect to time is minus omega squared times f. And we also notice there's a kind of a correspondence between applying the time derivative and multiplying the wave function by minus I omega. For waves of this simple kind, they amount to the same thing. Okay, armed with these things, we can now combine the wave equation that governs the way the wave behaves and our form of a simple wave, our complex simple wave, an amplitude times e to the I kx minus omega t, and let's see what we get. Well, we've done those derivatives, so we wind up with minus k squared times f is equal to minus omega squared over v squared times f, and if omega and k are positive, then we can just write this as omega equal to v times k. And that relation between omega and k, in fact, omega as a function of k, is what's called a dispersion relation. And we remember from our previous work on waves that dispersion relations are really useful. For example, the phase velocity of the wave, the speed at which a wave crest moves, is just the ratio omega over k, which equals the product of wavelength and frequency. And that turns out to be v for waves governed by the wave equation. And the group velocity, which is the speed of propagation of a localized group of waves, is the derivative of omega with respect to k, we found, and that's also v. The phase velocity and the group velocity are equal to each other for waves governed by this wave equation that we saw before. So for these mechanical waves, we started out with the wave equation, which for mechanical waves is always a version of Newton's second law, and we added to that this simple complex form for a wave function, and from this we derived a relationship between omega and k, a dispersion relation. Well, for quantum waves, we're going to sort of reverse the logic a little bit. We're going to start with a dispersion relation that we already know, a relation between omega and k for quantum waves, and we're going to add to it the idea that the wave might be of this simple complex form, a times e to the I kx minus omega t. And to make that work out, we're going to infer the wave equation that governs the quantum waves. So that's our goal for the rest of this lecture. So let's start out with some quantum waves in the form that we've been considering. Now, k and omega are related to the momentum and energy of the quantum particle described by this wave. So k is related to momentum. P equals h bar times k, where h bar is the usual Planck's constant divided by 2 pi. And we'll mostly see h bar in this lecture. And the energy, E, is equal to h bar times omega, h bar times the angular frequency. So that means that a relation between k and omega will be a relation between P and E. But we already know such a relation. And so let's see how we get we're going to apply that. How do we extract momentum information from the wave function? Well, how do we extract k from the wave function? We found that multiplying the wave function by I times k is about the same thing as applying the derivative. So what we can do is we can actually define what we'll call a momentum operator. It's minus I h bar times the derivative with respect to x. And the beautiful thing about this is that if you apply this operator to our wave function, then it's just like multiplying the wave function by the momentum of the particle. So this operator somehow extracts the momentum information out of the wave function. So there we have it, a momentum operator. And we can do the same thing for E, for energy. How would we extract energy information from the wave function? Well, to find out the energy information, we need to extract the frequency. And we know that if we multiply by minus I times the frequency, that's just like applying the time derivative. So we'll define an energy operator, which is I times h bar times the derivative with respect to time. And if we apply that energy operator to our wave function, it has the net effect of multiplying the wave function by the energy. So we have an energy operator, a way of extracting energy information about the quantum particle from the wave function. And it has the form of an operator. It's something that you do to the wave function, and for a wave function of this type, it simply is the same thing as multiplying by the energy. Now, I mentioned before that we already know a relation between k and omega. It's the same as the relation between p and e. That is to say, our dispersion relation is actually the relation p squared over 2m equal to e. We're right now talking only about a free particle moving in one dimension. And so this should be true as an operator relation if we apply the p operator twice and the e operator once to the wave equation. That is to say, 1 over 2m times the p operator acting on the p operator acting on psi should be equal to the e operator acting on psi. And if that's true, then we have the following remarkable equation. It's called the Schrodinger equation. Minus h bar squared over 2m times the second derivative of psi with respect to x is equal to I times h bar times the first derivative of psi with respect to time. Now, this is really important. Let's first of all remember the limitations of this. This is only for a free particle, a particle without any forces acting on it, moving in one dimension. But it tells us quite a lot. It is, in fact, the wave equation, the equation of motion for the quantum wave function. And in fact, we notice that we reverse engineered this in the same way, or we reverse engineered it from the dispersion relation, the relation between momentum and energy. Notice that the Schrodinger equation is a complex equation. It involves I. I appears right there in the equation. And that means that in general, we will need complex solutions. The wave function must be complex, which is one of the weird things about quantum mechanics. And finally, notice that the Schrodinger equation is based on energy, not force. And that tells us that energy is actually more fundamental in quantum mechanics than the idea of a force. Energy is what we need to think about. Well, this is for a free particle, a particle that has no forces acting on it. What if we wanted to consider a particle that had a force acting on it? Well, then we would have to make sure we describe that force in energy terms. In other words, we'd have to use a potential energy function. So this is the version of the Schrodinger equation that applies for a particle moving in one dimension subject to a potential energy function, u of x. That is to say, we're considering a conservative force with a potential energy function u. And we're basing this equation on the energy relation p squared over 2m plus u is equal to e. And so the Schrodinger equation in this case is minus h bar squared over 2m times the second derivative of psi with respect to x plus u times psi is equal to I h bar times the derivative of psi with respect to time. Pretty amazing. And so a typical kind of problem you would have here is somebody tells you what the force is. They tell you the potential function. It's a harmonic oscillator or a gravity field or something, and your job is to find solutions for the quantum wave function, that is to say, solutions to this equation given that potential function. Now, we can also apply these ideas to standing waves. Now you remember what standing waves are. In our situation, a standing wave, psi of x and t, will be some psi of x times an oscillation e to the minus I omega t. That is to say, we'll have a fixed spatial pattern given by psi of x. And there's also an oscillation frequency, omega, which will tell how things dependent on time. But the spatial pattern itself doesn't change in time. It just oscillates in a fixed way. So what happens for standing waves in quantum theory? Well, the first thing that we notice is that the probability density for the particle is the square of the magnitude of the wave function. But when we look at this kind of wave function, we find out that there is no time dependence in the probability density. The probability density just matches it's just the square of the spatial pattern, and it doesn't depend on time. None of the probabilities change over time when we look at where things are likely to be found. And similarly, if we look at the energy operator acting on a standing wave, then we just get a factor of h bar omega times psi. So the energy of this standing wave is just h bar times its omega. Its oscillation frequency is simply related to its energy. So to sum it up, a standing wave function, psi, represents a stationary state. We can completely describe it by that spatial pattern. And it's also a state of definite energy. These three ideas in quantum theory are the same idea. A standing wave, a stationary state, one whose probability distribution does not change in time, and a state of definite energy. These three things are the same thing in quantum theory. Okay, so suppose we have a standing wave pattern where the omega is related to energy in the usual way. Then what does the Schrodinger equation tell us about these standing wave patterns? This had better be a solution to the Schrodinger equation. That's the equation of motion in quantum theory. Well, if we write down the Schrodinger equation and we apply it to this pattern, we notice a couple of things. First of all, the spatial derivative ignores that e to the minus I omega t. And secondly, that e to the minus I omega t just shows up in every term. So in fact, if we divide by that, we wind up with the following equation. It's called the time-independent Schrodinger equation. It's an equation not for the whole wave function, but just for that spatial pattern part, that psi of x. And it's minus h bar squared over 2m times the second derivative of psi with respect to x, plus u times psi is equal to the energy times psi. Now notice that's a total derivative in one dimension because psi only depends on x. This is a remarkable equation and very powerful, very useful. It's the equation that has to be satisfied for a state of definite energy. That is to say, a standing wave or a stationary state in quantum mechanics. Okay, so let's take a look at this time-independent Schrodinger equation and see what it tells us. First of all, obviously, it does not involve time. Time is nowhere there. The psi there is the standing wave pattern that doesn't depend on time. And this is an equation for that standing wave pattern given a potential energy u of x. And it's a real equation. Notice that the imaginary unit I appears nowhere in this equation. So that means that we're going to be able to find real solutions to this. The wave function is complex, but all that complex stuff is in that e to the minus I omega t factor. If we're only interested in the standing wave patterns, we can just concentrate on real standing wave patterns. And often, it turns out we can only find sensible solutions to this equation only for certain discrete values of the energy E that appears on the right-hand side. And that means that only certain discrete energy levels are possible for the system. Now, we, of course, have seen that before in the particle in a box. And we can apply the Schrodinger equation to see how that works out. The potential in question is 0 if you're inside the box between 0 and L, and it's infinity otherwise. It's infinite. So there's no amount of energy you can have that would get you outside of the box. So this is sometimes called an infinite square well, and the particle just bounces back and forth between these impenetrable walls of potential energy. And so we can apply the time-independent Schrodinger equation to find the standing wave patterns. And what we find is that outside the box, the only way to solve this is for the wave function to be 0. So the wave function must be 0 outside the box, otherwise it's just impossible to solve the Schrodinger equation because that potential is infinite. The only way this could be equal is if psi were actually 0. Inside the box, the potential is 0, and we just have something where the second derivative of psi is proportional to psi, and a sine of k times x is a solution to that. Of course, in order for the wave function to be continuous, it has to be 0 at the walls, because it's 0 everywhere outside. So psi of 0 is equal to psi of L equal to 0. The sine function automatically is 0 at x equal to 0. But what about at L equal to 0? Well, the only way that can happen is if k times L is equal to n times pi, where n is 1 or 2 or 3 and so on. K times L is equal to n times pi. So these are the solutions to the wave function for the particle in a box. They look sort of like something like this. Now, what does the Schrodinger equation, time-independent Schrodinger equation, tell us further? Well, u is equal to 0 inside the box, and so the left-hand side, when I take that second derivative of the sine function, I get minus the sine function, and so I just get h bar squared times k squared over 2m times the wave function is equal to e times the wave function, which means that h bar k squared over 2m is equal to e. But only certain values of k are possible. K is equal to n pi over L, where n is equal to 1, 2, 3, and so on. So that tells us that only certain values of E are possible to get a sensible solution to the time-independent Schrodinger equation. And in particular, those solutions are h bar squared times pi squared over 2m L squared times n squared. I just took h bar squared over 2m and I multiplied it by k squared, which is pi n over L times squared. This doesn't look quite as familiar as it might, but if we write it in terms of Planck's constant, h, instead of the reduced constant, h bar, then we get that this is h squared over 8ml squared times n squared, where n is equal to 1 or 2 or 3. It's a positive, non-zero integer. Okay, so we can see how the particle in a box is really an expression of the time-independent Schrodinger equation, the equation that must be satisfied by standing wave patterns for quantum waves, the states of definite energy, the stationary states of the system. And that's the lecture for this time. So I'll see you in class on Wednesday, and we'll talk more about the Schrodinger equation and the time-independent Schrodinger equation. See you then.